In this video, I'm going to show the image of why we prefer differential signaling from a circuit and system perspective. In the why SerDes video, we show how the SerDes advantage with just one wire is. That must be applied with a single-ended signaling, but most high-speed SerDes still prefer applying the differential signaling by extra one wire. Why? Before understanding why, let's look at the difference between single-ended and differential signaling. The first obvious item is the physical difference. For example, on-chip pin count would be 1 versus 2. Off-chip channel number would be 1 versus 2. Therefore, if both single-ended and differential signaling operate at the same data rate, the single-ended has a twice I/O bandwidth density as the differential signaling. Or at the same I/O bandwidth density or throughput, the single-ended signaling can operate at only half the data rate of the differential signaling, like 5 gigabit per second versus 10 gigabit per second here. At this moment, I guess you may think the single-ended signaling is the best for area, complexity, and data rate throughput, so we should use it, right? However, there are numerous signal integrity and the circuit design changes with single-ended signaling. The most obvious one is lower crosstalk immunity. As you can see, the single-ended aggressor will easily interfere with its adjacent single-ended victim, and the corresponding single-ended victim would not have good immunity. Then, you cause the big error in the link easily. How is the differential signaling? Is the differential victim having a better crosstalk immunity? Think about your crosstalk image for 5 seconds. Bingo! The answer is yes, but why? Here is the differential crosstalk image. As you can see, the single-ended aggressor will interfere with its adjacent differential-ended victim, but the crosstalk strength and phase should be almost the same at the positive and negative pin, which is so-called common mode interference or noise. Since the differential signaling would only care about the voltage difference between the positive and negative pin, the delta V crosstalk would be very little. That's why the corresponding differential-ended victim would have very good immunity and maintain a very low bit error rate in the link. Another single-ended signaling issue is the simultaneous switching output event, which is called SSO. For example, multiple links should have a single VDD supply or ground connected not only at the TX side, but also at the RX side. Furthermore, the inductor wire inevitably throws on-chip supplies or ground to the off-chip package and PCB trays. As the input of the TX toggles, the switching current may result in a big voltage drop at the inductor of each supply and ground pin. Furthermore, the return ground path between the TX and RX could be a big inductor and the switching ripple could be even worse. Those SSO at the supply and ground will degrade the signal integrity at the RX input and cause big error easily. Again, how can the differential signaling do better? Think about your SSO image for 5 seconds. Yeah, you may have an image that the inductor would be still there. The only way of reducing the self-introduced power supply ripple across it is to reduce the current. Your last SSO image should be less switching current leading to fewer voltage ripples, but people may have a concern about the noise margin in terms of the reduced current, right? What can we do? Beauty of the differential signaling is doubling the effective swing And let's review the swing images here. In single-ended signaling, the maximum swing is VDD to ground, but differential signaling only considers the differential level between the positive and negative pin. As you can see, the TXP swing is a half VDD, and the TXN swing is also a half VDD, but its polarity is negative over the TXP. Then we take the difference signal level under the IXP and IXN. The delta Vx will be VDD as well. So even we reduce the signal swing under each TXP or TXN to be half over the single-ended one, the equivalent swing of the differential signaling is still the same as the single-ended signaling. The differential signaling also mitigates the return ground path SSO issue, and we will talk about that in detail later. The last single-ended change would be the reference level of the receiver. For example, the input of the receiver would be toggled between VDD, supply, and ground. So the reference voltage is a must to set a logical 1 or a logical 0 for the receiver as a slicer or an analog-to-digital conversion. This reference is obvious to be half of VDD with the best noise margin. However, the reference voltage generation may include a noise, which will reduce the noise margin and cause a higher bit error rate. In addition, the reference should be shared in multiple links to save area and pin counts. The reference distribution may introduce more crosstalk, resist voltage drops, and matching impairments, etc. So, the signal integrity at the reference voltage will cause a high bit error rate. Lastly, what is the differential signal reference? The last one you should have is a good reference image on your head. Yes, the 0 voltage is the reference level for differential signaling. For example, the polarity of a delta Vx would be the IXP minus IXN, which is a logical 1 if the delta Vx is greater than 0, and vice versa. So, there's no need to generate any required voltage level. The beauty of the self-reference level is it has an immunity of crosstalk, common mode noise, and receive voltage drops concerns than any other voltage reference. But the self-reference is very critical in matching between the positive and negative pin. To be clear, the common mode interference would be zero effect since both IXP and IXN are seeing the same interference. So the interference signal of the delta Vx would be 0. But if there's a mismatch between the positive and negative pin, then the interference of the differential signal delta Vx will not be 0. We will describe the matching in detail later. Here is a summarized image you may have for why we prefer a differential signaling in a link, especially a very high data rate. First, the differential signaling would only care about the voltage difference between the positive and negative pin. So, the differential ended victim would have very good immunity and maintain a very low bit error rate in the link, even at a high vary frequency. Second, the differential signaling self-introduced power supply ripple can be reduced by reducing its switching current but maintaining the equivalent swing for noise margin. Lastly, the 0 or the self-reference level of the differential signaling will mitigate the reference distribution issue, and there is no challenge of generating any required voltage level. I hope those summary images provide you with a ballpark idea of why the differential signaling is more popular. But does not mean the single-ended cannot meet the system link target. In general, single-ended signaling is just more difficult to handle all those issues. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may be benefit from it.